У перший день конференції було перше засідання секції нашої, і були всі доповіді. Володимир Щедрик, який згадав, що методи факторизації поліноміальних матриць чи матричних поліномів, розроблені у відділі алгебри Петром Степановичем Казимірським, можна застосувати і в іншій галузі математики, зокрема алгебри. І він показав, що, застосувавши ці результати, описав повні лінійні групи матрич другого і третього порядку, тобто теорії груп. В доповіді Богдан Шеворовський розглянув напівскалярну еквівалентність матриць, її простішу форму відносно таких перетворень, і що ця форма застосовується до відомої проблеми пар матрич, тобто класифікації пар матрич над полем відносно подібності перетворення. Сьогодні ми наведемо ще одне застосування цих результатів, зокрема, до розв'язування відомого рівняння, поліноміального рівняння типу Сильвестра, рівняння 5. В відділі розроблялися методи дослідження структури матриць відносно різних типів еквівалентності. І, зокрема, була встановлена така стандартна форма відносно напівскалярної еквівалентності, це трикутна форма з варіантними множниками на головних діагоналях. Вона названа стандартною, бо вона не є канонічною. Зрозуміло, що та задача не розв'язана повністю, бо містить, зокрема, проблему подібності пар матриць. Отже, ця форма була використана Петром Степановичем за його ж висловленням одним із методів до розв'язання проблеми виділення регулярних множників із матричних многочленів. Ми сьогодні розглянемо якраз розроблений метод розв'язування матричного поліноміального рівняння Сильвестра, побудова розв'язків на основі цього, описання його структури. Нагадаємо, що всі результати, переважно, які стосувалися цього рівняння, були у випадках, коли матриці А від лямбда, Б від лямбда, коефіцієнти матриці регулярні обидві або принаймні одна. Ми розглядаємо це рівняння в загальному випадку, коли обидві матриці є нерегулярні. Описуємо розв'язки при допомозі цього способу. Надалі я передаю слово співавтору результатів і співдоповідачу Наталії Дzalyuk. Вона більш докладно розкаже про ці результати.
Дякую, Василь Петрович. Okay, please take mouse. Good day. My name is Natalia Dzalyuk, and I present a report together with Professor Vasyl Petrychkovych. In this very hard time in our country, we thank our armed forces of Ukraine for the opportunity to present our report. The title you see, and Sylvester-type matrix equations are the matrix linear bilateral equations with one variable x, equation 1, and with two variables x and y, equation 2. General linear bilateral equation with one variable x in the form 3 is called general Sylvester matrix equation, because Sylvester was the first who studied this equation. Use the concept of Kronecker product or direct product of matrices. Equation 3 over a field F can be reduced to equation 4. Methods for solving equation 4 is well known. Matrix equations of different types appear in various branches of mathematics, physics, mechanics, etc. Linear matrix equation, in particular, or Sylvester-type matrix equation over different domains apply in solving problems of dynamical system theory, control theory, stability theory, and in other problems. Solvability conditions of linear matrix equations 1 and 2 over a field F and over a ring of polynomials f of lambda was proved by Rode. Solvability conditions are the criterion for the solvability over source rings in which the criterion for the equivalence of matrices is formulated. For example, over a field, over a ring of polynomials, over an adequate ring, and in general over a ring of elementary divisors. Many authors extended the Rode theorem to the case of principal ideal rings, arbitrary commutative rings, other rings, and for other matrix equation and system of matrix equation. Futorny, Klimchuk, Serhinchuk, Dmitryshin, Kakstrom, for other matrix equation and system equation. In addition to solvability, in addition to the solvability conditions, solutions with certain properties are also required. Consider the polynomial Sylvester-type matrix equation. Barnett studied the conditions for relatively primes of two polynomial matrices. And in connection with this, he established the condition for the existence and uniqueness of the solutions of bounded degree. Let us formulate the Barnett theorem as follows, this corollary. The Sylvester matrix polynomial equation 5, where A and B are regular polynomial matrices, and for C is satisfied this condition, has a unique solution x, y, such that degree of x less than degree of B, degree of y less than degree of A, if and only if their determinants are relatively prime. Note that if the matrix polynomial equation 5 is solvable, it has solutions of unbounded above degree. So we have the following natural questions. What is the minimal degree of solutions of this matrix polynomial equation? Feinstein and Barnes Feinstein and Barnes generalized the Barnett result in the case at least one, but not necessarily both, of matrices A and B are regular. Apply the concept of companion matrices of matrix polynomial to the equation 5-stroke. In this way, this equation 5-stroke can be reduced to the matrix equation 6-stroke with one variable z over field f. This approach used by Petrychkovych to establish the next result. The equation 5-stroke, where A and B are monic regular matrices, has a unique solution x0, y0, where degree of matrix x0 less than degree of matrix B, if and only if their determinants are relatively prime. In this paper, for the linear matrix equation 2 over the field of complex numbers C, the formulas for solutions of maximum and minimum rank are obtained. And some results for a system of this equation are established. We investigate solutions of Sylvester-type matrix polynomial equation 5, where both matrix coefficients A and B are non-regular matrices. We describe the row and column structure of solutions of this equation by using the standard form of the collection of polynomial matrices with respect to semi-scalar equivalence. A criterion for uniqueness of such solutions is pointed out. We also propose the method for construction of solutions of this matrix polynomial equation. So, recall the definition. Collection of polynomial matrices are called semi-scalar equivalent if there exists a scalar matrix Q and invertible matrices Ri, such that Bi equal Q, Ai, Ri, I equal 1 dot K. This concept was introduced by Kazimierski and Petrychkovych for polynomial matrices over an algebraically closed field of characteristic 0 in first paper. And generalized for matrices over an arbitrary field in the second paper. Much later, the similar result was obtained by Dias da Silva and Lafay. Based on the standard forms of polynomial matrices with respect to semi-scalar equivalence, methods for factorization of polynomial matrices over different fields were developed by Kazimierski and Petrychkovych in first and second papers. And they were also applied to the well-known matrix pair problem by Shawarowski. Pair of non-singular polynomial matrices A and B from matrix polynomial equation 5 is a semi-scalar equivalent to the pair of triangular matrices TA, TB in the standard form. TA is lower triangular matrices with invariant factors on the main diagonal, and TB is lower triangular matrices with the variant factors of matrix B on the main diagonal. Then, from equation 5, we have equation 6. This is associated equation, and X tilde, Y tilde, and C tilde are matrices of the following forms. My idea of our methods is as follows. From matrix equation 5, we have a matrix equation 6, and this matrix equation 6 is equivalent to the system of equation 7. And from a solution of this system of equation 7, we have equation 8. This is solution 8. This is solution of the matrix equation 6. And we have solutions 9. This is solution of the matrix equation 6. This approach allowed us to obtain the following results. Theorem 1. In this theorem, we describe the row structure of the second component of solution and column structure of the first component of solution of the matrix polynomial equation 6. In theorem 2, we proved the existence of solutions with bounded degrees in the case where coefficients A and B are non-regular for matrix polynomial equation 5. Matrix polynomial equation 5 has solution x1, y1 such that degree of second component y1 less than degree of Smith normal forms of matrix A, and solution x2, y2 such that degree of x2 less than degree of Smith normal forms of matrix B. In the next result, in theorem 3, we generalized results of Barnett and Feinstein-Barnes, where matrices A and B are non-singular only. That is, it's not required that both or less of one of matrix A and B be regular. And theorem 4. And theorem 4, we also establish the existence criterion for unique solution of bounded degree for the component of for one component of matrix polynomial equation 6. And in theorem 5, we establish the existence criterion of unique solution of bounded degree for both components of matrix polynomial equation under the condition that their determinants are relatively prime. We know that the matrix polynomial equation has solutions of bounded degrees. And what exactly can this degree be? Next, we establish the necessary and sufficient condition for the existence of solutions x, y of given degrees k and l respectively for the Sylvester matrix polynomial equation 5. Let's write the coefficients a, b, and c from matrix polynomial equation in the form of matrix polynomial. Here, A has a degree R, B has a degree S, and C has a degree T. Necessary condition for the existence of solutions X, Y of given degree K, L is the maximum of sums of degree matrix A and X and B and Y greater than or equal degree of matrix C. Using the Kronecker product of matrices from coefficients AI and Bj of matrix polynomials A and B, we construct block matrices GA in the form 10 and block matrices JB in the form 11. Where 0 is a zero matrix of the suitable size and symbol T denotes the transposition of corresponding matrices. From matrices JA and JB in the form 10 and 11, we construct matrices JA, A equal 1, 2, 3 of this size. With respect to relationship between the degrees of coefficients A, B, and solutions X, Y, matrices JA and JB can have different count of rows. Therefore, we get the following cases. If R plus K equal S plus L, then J1 has the form 12. If R plus K greater than S plus L, then J2 have the form 13. And if R plus K less than S plus L, then J3 can the form 14. Okay, and theorem 6. And theorem 6. In theorem 6, we established the necessary and sufficient condition for the existence of solutions of given degrees for Sylvester matrix polynomial equation 5. Matrix polynomial equation 5 has solutions x, y, respectively, if and only if a rank of matrix Ji equal rank of matrix JIC, where the matrix Ji has one of the forms 12, 13, or 14, with respect to relationships between the degrees of coefficients A, B, and solutions X, Y, and column C is in this form. Okay, then the methods for construction these solutions. these solutions are constructed from the solutions of the linear equation systems, over a field F, where X and Y have the following forms, and C is in the following form. Okay. A more general formulation of theorem 6, if the maximum of sums A and X and B and Y greater than or equal degree of C can be found in our paper. Okay. And consider the matrix equation 2 over adequate ring. We propose a method for solving matrix linear equation 2 over adequate ring by means of standard form of pair of matrices with respect to generalized equivalence. We establish the formulas of general solution of the criterion of uniqueness of particular solutions of such matrix equation. Recall that R is called an adequate ring if R is commutative domain of the integrity in which every finitely generated ideal is principal, and for any elements A, B, where A not equal 0, the element can be represented in the form A equals C multiplied by D, where greater common divisor C and B equal 1. So there are relatively prime, and D, I, and B, greater common divisor not equal 1 for any not unit factor Di of the element D. Okay, by Helmert. By Helmert. Okay, recall the definition. The pairs of matrices are called generalized equivalent if AI equal U V I B I for some invertible matrices U and V over the ring R. This concept introduced by Petrychkovych and Vasyl Petrychkovych established a standard form with respect to generalized equivalence. Okay, let matrices A and B be non-singular, and SA, SB be their Smith normal forms. Then the pair AB is equivalent to the pair SATB in standard form. If the pair of matrices AB is generalized equivalent to the pair of diagonal matrices SA, SB, then it is called diagonalizable. And Vasyl Petrychkovych established the diagonalizability criterion. And sufficient condition under which the pair of matrices AB is diagonalizable. Okay, and the main idea of our methods is let the pair of matrices be diagonalizable, and then from matrix equation 2 we have matrix equation 15, where X tilde, Y tilde, and C tilde have these forms. And our theorem 7, let X0 tilde, Y0 tilde be a particular solution of matrix equation 15. The general solution of this matrix equation has this form, where WC and W phi is matrices in this form. Phi is Smith form of matrix A, Psi is Smith form of matrix B, and R R, D, IJ, Rm denotes a completely set of residues modulo M. The general solution of matrix equation 2 is in this form. Okay, and the last theorem. The theorem 8 gives the unique criterion for the particular solution of the matrix equation 15. Therefore, in theorem 9, we have solution x0 tilde y0 tilde. This is the general solution of this matrix equation. And x, y, general solution of matrix equation 2 over adequate ring. There are the list of our papers in which we mention the results. And thank you for your attention. І слава Україні!
Thanks for your report.